Welcome to another session of our reading group on the assumptions of physics. We are gonna, as usual, wait a minute to see if other people show up and review where we were. And I will also share the link to the book. Today we can't use the automatic build because somehow it's not working. And I need to share the text. Share. There we go. Where is it? It's this one. Okay. So last time, if I remember correctly, we were looking at essentially how relativistic ideas show up without adding any assumptions, just by assuming determinism, reversibility, the independence of the degree of freedom, and the kinematic equivalence. I think today we have the last bit to see essentially why Galilean relativity fails, which basically fails to count states properly, and then, oh, there is something else about the metric tensor. And then we are going to finally look at why do we have phase space, why we have conjugate quantities, why we have position and momentum. So I'd say let's just go through it. Artem, want to start?
Yep. So the failure of Galilean relativity, given that our assumptions led directly to relativistic mechanics, non-relativistic mechanics must fail to satisfy the strong kinematic assumption. We have not identified the exact reason of the failure, though we have identified an interesting issue. Galilean spacetime transformation correspond to, we have that.
Yeah, the time is the same, and the position gets translated with the velocity, and the velocity just adds a constant.
Yeah. The canonical transformation induced by that space-time variable change is the following.
Yes, so here is we're basically changing the position in the same way, and the momentum change as covariant components. So you get P with the derivative of Q and Q hat, and minus E with the derivative of T and Q hat. So this part is zero because these are independent variables. And in this here instead, no, sorry, because t does not depend on q, like the transformation leaves the time the same, so this part is zero, and so you just have this part which is one because this is the same variable, like there is just, it's not the same variable, there is just it's the function that goes between the two is just a line. So the derivative of q with respect to q hat is 1. And then minus e is the time component. And this time, your derivative time with respect to the other time, which is the same variable. So you get a minus e. And q does depend on time, and therefore you get the minus v0p, right? So this is the transformation that you have if you make the canonical transformation.
Which gives us different rules for how momentum and energy transform. Note, for example, that the momentum remains unchanged. The expected rules would be, so the momentum increases by mv0, and so we have the energy, we have the increase in kinetic energy as well.
Right. So you would expect that you would use the same definition between P and V and E and V in both frames, and then use those as transformation rules, and you get something else. Tobias?
Okay. The difference between the two expressions is a constant. Therefore, Galilean change of variables together with non-relativistic expressions for momentum and energy are still canonical transformations. However, accommodating that constant requires a change of gauge. That is, if we start in an inertial frame where P is some multiple of the for velocity, or like the covariant for velocity, I guess.
Right. It's
We
basically the
end,
kinetic. This is the kinetic momentum.
yeah. We end up in another inertial frame where we have the same expression plus, well, I guess a gauge field, which has the specific expression.
Yeah, so
Okay.
we are basically changing the gauge by adding. So these differences, right? So here we have a difference between the expected. Where is it? So this is the p that we get, and this is the expected p, right? So we have this different on mv0.
Yeah.
We can absorb that into the vector potential and put it inside here. Right, this would be the spatial component of the vector potential, and we know that this is the general transform, like the general relationship between the momentum and the velocity, the kinetic momentum and the potential. So we can absorb that there, and we can do the same with the time part.
This is okay. This is the vector notation, right? The first entry is the energy
Correct. Yeah, yeah,
entry. Yeah, yeah,
yeah.
okay, I see.
This is the time part, and these are the spatial parts.
Yeah.
Right. So this is AT, and this is AQI.
Do we get the mixed term that pops up in the energy? Oh
The
no, sorry.
mixed
No, no, no.
term,
The V0P is is correct. The V0P also uh pops up in both expressions, what we expect and what we get.
yeah.
Okay. So yeah. Okay. So the new vector potential is still a constant field. Therefore, the forces do not change. Still, the spatial components have a different value than the time ones. Therefore, the direction of momentum is corrected. Mhm. Should I continue?
Yeah, sure, finish.
Uh, what we find then is that Galilean transformations do not preserve the relationship between kinetic momentum and conjugate momentum. To recover the original relationship, one has to perform a gauge transformation. But this is contrary to the expectation that the laws are the same for all inertial frames. There are likely other deeper issues at play, which we hope to uncover in the future.
Right. So this is a part that probably can still be done. So what it's not here, it's understanding. So the symplectic form should basically remain the same, right? What I haven't checked here if it's the new variables are still canonical, which I think it is. So that there might be other things that needs to be sort of rechecked, and then you might find other problems. But this is so far what I had figured out. Mark, want to continue? Or maybe it doesn't work the mic, so we can go back to Artem then.
Okay, so metric tensor revisited. As we saw, the metric tensor appears not
Sorry,
as
hi.
defined.
Oh,
Yeah, go on.
Oh, there's a huge delay. I thought
oh wow. Okay.
where
Okay, Artem, why don't you go?
Yeah, okay. So as we saw, the metric tensor
when we
appears.
at this. Yeah, okay. I'll skip.
The metric tensor appears not as defining the distances in spacetime, but rather as the linear relationship between velocity and conjugate momentum. It does, however, end up playing an important geometric role. in 1.159, we see that the metric tensor times the mass is the off-diagonal component of the form omega A. Therefore, if we have a range of positions dx alpha and a range of velocities dv beta, the number of configurations they identify is given by dx alpha times mass times the metric tensor times dv beta. In other words, inside 1.177, the metric tensor allows us to count states in terms of kinematic variables.
So this is an insight that I don't know how far it goes, but it seems from all of this that the real purpose, like the way that this metric tensor comes out, it's not there to give primarily a geometry to configuration space, but it's there to count states in position and momentum, in position and velocity, in kinematic variables.
Okay. This corroborates what we saw in 127. The determinant of the metric tensor is the Jacobian determinant that allows us to express densities over phase space as densities over kinematic variables. In relativity, the square root of the determinant of the metric tensor appears to create an invariant volume element. That is an integral over a region U with the square root of the determinant of the metric and then our little volume defines the volume of space-time region U. However, we can also define an invariant volume element over the space of kinematic variables. That is, we have an integral over a volume.
Yeah,
Here we
so that would be a
have
region of phase space.
Okay, now we have phase space. Now we don't have the square root, and we have space variables and velocity variables.
Right.
This defines the volume of the position velocity space. The determinant of the metric tensor then is more directly giving us the size of a volume taken in position velocity space instead of space-time. This also connects to the ability to specify distributions in terms of kinematic variables, since as we saw in what is that?
Full kinematic equivalent density.
Okay. The Jacobian determinant of the transformation between position and velocity is proportional to this determinant of the metric.
Robbie?
Is my turn?
Yeah.
Okay. Why is it then that defining volumes over kinematic quantities fixes the geometry of space-time? Note that both velocities and differentials of space transform like vectors, since du alpha equals the derivative of x alpha with respect to tau. Therefore, if that is invariant, okay, so just switching the last u for an x, then that will also be invariant. The geometry of space-time then is set up by the geometry of phase space. Should I just finish it?
Sure.
There are other interesting open questions to explore to better understand this relationship. For example, in relativity, one does put spatial and time variables on the same plane. However, we saw that the primary role of the metric tensor is so that we deal with distributions and integration, and these work differently in space and time. Consider, in fact, a distribution rho of position, velocity, and time. This would represent the evolution over time of a distribution over kinematic variables. At each time, the distribution has to integrate to 1, assuming it is normalized, which means the units of rho are 1 over distance cubed and velocity cubed, the inverse of the cube of distance times velocity. Note that every observer has to see the same thing, a normalized distribution at each moment in time. Additionally, this has to happen no matter what rho is. An open question in reverse physics, then, is whether imposing this requirement is already enough to recover parts of relativity.
Right, so this is something that it's still an open problem for me. I feel that there should be a way to do it. I've never found it. So if you even just imagine in space, right? So you have a space that flows through time, and you have a probability distribution that flows through time. Every spatial cut, if you have any spatial surface, has to integrate to one. But if you go in time, there is no integration to one of the probability over time, because you are always going to be somewhere in time. So the fact that you have to integrate to one along every essentially spatial surface, but not along time, should give you some constraint on how tilted the spatial surface can be, because at some point you're going to become vertical and integrate over time. And that would be a way to understand why there is the cone of the speed of light, that you can't tilt too much, because otherwise you're switching your variables of integration. So I feel that there should be a way from just this constraint to recover the Minkowski metric. I was never able to apply it correctly, and if anybody wants to try and then teach me how to do it, but there should be a way to do it. I really feel that there should be enough. And Tobias, we talked about a little bit about this. Okay, so if there are no other questions about this, we can just go to the new part, which I actually, it is very important to me. Like why do we get position and momentum? Why we get conjugate quantities?
So Robbie was last, right?
Yeah.
Okay, so reverse and phase space. In this section, we will find the assumptions required to rederive the structure of phase space. The principle of relativity will play a key role, as the structure of classical phase space is the only structure that allows us to define densities and entropy in a way that is coordinate invariant. Properties of phase space. We have seen that determinism and reversibility and independence of degrees of freedom are the constitutive assumptions of Hamiltonian mechanics, in the sense that they fully characterize Hamiltonian evolution. The addition of kinematic equivalence in its full version recovers both Lagrangian mechanics and massive particles under potential forces. The relativistic version of the theories comes out without additional assumptions, simply by properly dividing the role of time as a variable from time as a parameter. But in all this discussion, we assumed without questioning that states are identified by pairs of variables, position velocity or position momentum. Is this a coincidence, or is this an underlying reason for it? Can we find assumptions from which the structure of phase space itself can be recovered?
Since we are interested in the structure of phase space itself, let's go back to its original version without the extension to time or the temporal degrees of freedom, or the temporal degree of freedom. Throughout the whole discussion, conjugate momentum pi has been written with the index down, tacitly assuming it to be a covector. This means it obeys the following transformation rules under coordinate changes.
So q hat are the new coordinates, are the new positions, and
Yeah.
p hat are the new momentum, which basically are the old momentum multiplied by the Jacobian, actually the inverse of the Jacobian of position.
Yeah. Okay. When a metric tensor is defined, That is when the assumption of kinematic equivalence is valid. The difference between vector and covector blurs, as we can always transform one into the other, but this is not the general case. We have, therefore, this condition. Conjugate momentum pi changes like a covector under changes of coordinates qi, which characterizes the relationship between qi and pi. We want to stress that these changes of coordinates do not mix space and time variables. Therefore, we are only talking different choices of spatial coordinates at equal time.
I think
Taking
it's
different
taking,
choices.
yeah, I think
Yeah,
it's taking.
taking different choices of spatial coordinates at equal time.
Mark, want to try?
Yep, okay. Given that the form omega AB plays a fundamental role as it defines the geometry of phase space in terms of state count, let's see how it transforms during a coordinate change. We have, okay, that's going to be a lot. Omega hat AB equals.
I can go through
should I
it. I
really?
can go through it.
Yeah, okay.
So this is the new omega, right? So these are the components
omega hat,
in the new coordinates. And now we have to change each components, and so you basically get the Jacobians on one side and the Jacobians on the other side with the indices that are matched correctly, right? So this changes this k to an I, and this part will change this L to a J, and you're going from the old components to the new from the old coordinates to the new coordinates, right? And you're changing both for the Q's and the P's. Then what happens here is that the new Q's only depends on the old Q's. They do not depend on the old P's. So this part is 0. And we saw that the new P's depend from the old P's with the inverse Jacobian between the Q's. And the same thing is going to be on this side, is just that this is transposed. Right? So you have this 0, and then you have, these are the cross term. This is how the new P's depend from the old Q's. Then this is just a symplectic form, so it's 0, 0, 1, 1. And so you have this Kronecker delta here. The Kronecker deltas are just going to change the L to K's. And so when we are contracting, I think I'm contracting this part with this part, yes. You are gonna basically, switch the sides and switch the K to the L's. So this is what you get just computationally, and then you just have these two things. You multiply together and you get this horrible thing. And then what happens when you're making this multiplication? You see that you are contracting a QL with a QL. So this, by the chain rule, just becomes the Jacobian between the Q hat J and the Q hat I. And similar things happen here. Every multiplication is going to contract in some way. And then, since this is the Jacobian between the same things, these are just going to be Kronecker deltas, and then you need that this part has to be 0.
Okay. For the last step, we are taking partial derivatives on the new variables with respect to the new variables. The derivative is equal to 1 if we are taking the partial derivative with respect to the same variable and 0 otherwise. We find that condition, the form omega AB is invariant under the changes of coordinates qi, ps sim, is implied by ps cov.
Okay, so we again, in the usual reverse physics thing, we have one condition and we try to prove equivalence. Robbie?
As usual, we ask whether the converse is true. That is, suppose we perform a change of coordinates Q to Q hat for which omega AB is invariant. Does this pose restrictions on how conjugate momentum changes? We have
So similar thing here, up to here it's going to be the same, right? But now we are imposing, we're not calculating this part because we do not know how how what this, we don't know that this part corresponds to the Jacobian, so we can't make that substitution there, and so we get this is now a constraint, that this is equal to 0 becomes a constraint. Actually, sorry, that this is equal to the Kronecker delta becomes a constraint.
Notation wise, would it make sense to put like a exclamation point over that equals, just to say impose or something like that? Like a must be equal rather than a equal?
Right, so this is like the starting condition is that this is going to be equal to here, right? So
Yeah.
I never know quite how to disambiguate between the equal meaning a calculation and the equal means that we're putting there. So you say with an exclamation mark equal. I've never seen that notation actually.
Yeah, I've seen like a colon equals for definition, and then an exclamation point equal for like this must be, like we say it must be so or something.
Oh, I never seen that. Interesting. So that, yeah, then we would have to go and relook all the book to make the whole thing consistent. It's a
Yeah.
project.
Yeah. I mean, it's up to you. You don't have to.
No, it could be like something like that could be. So there are some elements of reverse physics that I think could be done better. So one of the things that I've come to realize a lot more cleanly also by looking at reverse mathematics and talking to people that are reverse mathematics, that it would be much better if it was clear every time that we prove an equivalence, what is the base theory. So what are the things that are underlined such that we can define the two sentences and then prove the equivalence within the base theory, right? So when you want to prove the equivalence between the axiom of choice and Zorn's lemma, you're assuming ZF as your base theory for set theory, and then you prove equivalence within that base theory. So in principle, all of this could be done a lot better by clarifying all these issues. That would basically again be a separate project. So that there is still a lot of room for improvement of how to do reverse physics, because this was the first time that we actually got things going, right? And
Yeah,
so
makes sense.
the meta way, the meta reasoning of how to do it was not there at the time.
Yeah.
okay. So from this, we have the two off-diagonal terms impose the same constraint. In matrix terms, we are taking the product of two matrices and equating it to the identity matrix. Therefore, the two matrices are the inverse of each other.
So
the
now we
part-
basically are recovering that the way that the new momentum depends on the old momentum is through the inverse of the Jacobian.
This means that the change of position variables induce a change of momentum.
And again, you have this linear term given by that plus the arbitrary functions.
Where a sub j are arbitrary functions, which we can set to 0 without loss of generality. We have a footnote. The arbitrary functions change the value of 0 momentum, potentially at every point in a different way. While this is mathematically possible, it would make no physical sense that a coordinate change would induce a change in the 0 reference for momentum. We will see later how this is related to gauge transformations. Back to the main text. This makes momentum a covector.
The second constraint comes from the bottom diagonal term. Using the newly found transformation rules we have, and that term.
Yeah, so
Okay,
you were
what's the
basically substituting it here, and then when you substitute it here, you have this QL that simplifies, and then you're also substituting it here, and then you are going to have this QL and QL that simplify, and then now these two are the same thing.
This constraint is satisfied simply because position and momentum are different state variables, and partial derivatives along one variable are taken, keeping the others constant. By imposing the preservation of the form omega AB under an arbitrary change of coordinates, we recover the transformation law of momentum as a covector. Therefore, conditions PS, okay, let me say that in PS was phase space, right?
Yeah, PS is phase space.
A phase space, and that's the covariance of momentum.
Yeah.
And the second one is like the invariance of the symplectic form are equivalent. The invariance of the form omega AB under coordinate changes means that all those properties that were invariant under Hamiltonian evolution are also invariant under equal time coordinate changes. Therefore, the condition T plus on brackets are invariant under equal time coordinate changes is equivalent to the invariance of the symplectic form.
The following conditions are equivalent to each other and are simplified by the phase-space symplectic form assumption, but do not imply it. The system allows statistically independent distributions over each degree of freedom under any choice of coordinates qi. The system allows informationally independent distributions over each degree of freedom under any choice of coordinates qi. The system allows peak distributions where the uncertainty is the product of the uncertainty on each degree of freedom under any choice of coordinates qi. Physically, these correspond to the independence of degrees of freedom, which is assumption IND. The only difference is that the assumption must be valid for all equal time coordinate changes, which is just an application of the principle of relativity.
If you guys recall, many weeks ago, we discussed these conditions during the evolution, right? We were saying that during evolution, we can still have essentially you can have this density distribution that are independent, and even in the future you can always have this distribution being independent. Now we're basically making similar conditions but under just coordinate transformation.
Lastly, the following conditions are all equivalent but independent of the PSI conditions and are implied by the symplectic structure but do not imply it. Phase space volumes are invariant under equal time changes of coordinates qi, that's PSV ball. Then the Jacobian for the transformation induced by equal time changes of coordinates qi is unitary. That's PSV Jack for Jacobian. Densities over phase space are invariant under equal time changes of coordinates qi. That's PSV den. Densities. Thermodynamic entropy is invariant under the equal time changes of coordinates qi. PSV thermodynamic. Information entropy is invariant under equal time changes of coordinates qi. PSV info, information. Uncertainty of peak distributions is invariant under equal time changes qi. PSV unc, I guess, uncertainty. Physically, this corresponds to requiring that the count of states is the same under all choices of coordinates at a given time. In the same way that conservation of omega AB in time was equivalent to assumptions dr and int combined, any PSV condition together with any PSI condition will be equivalent to any PS condition. That is, the phase space structure corresponds to the invariance of space count plus independence of the degrees of freedoms.
It should be evident that all these properties are necessary if we want to have a physically meaningful state space. If state count, densities, entropy, independence of degrees of freedom were not properties that all equal time observers could agree on, there would be no notion of an objective state to begin with, and it would be pointless to even talk about isolation, determinism, thermodynamics, and so on. All these properties, then, are constitutive assumptions for any state space, as without them there are no well-defined states. Having established that phase space has all these properties, do these properties define phase space? That is, suppose the states of our system are identified by a finite number of continuous quantities, meaning that this state space is a manifold. Does the invariance of those properties constrain that space to be a phase space?
Okay, so to recap, we basically said that if we got these conditions of invariance of state counts, entropy, essentially volumes, and invariance on the independence, we get the symplectic form, right? But the question is that we're still working with the idea that there are pairs of quantities. So now we basically want to say, can we recover even the idea that we have pairs of quantities just from these assumptions that we already have, or we need an extra assumption to tell us that we have pairs? That's what we're trying to find out.
Invariance over the continuum. To simplify the matter, let us consider the case of a single degree of freedom. One way to define the problem is to ask if a distribution is uniform for one observer. It should be uniform for all equal time observers. Uniform distributions are important in statistical mechanics since the macrostate of an isolated system is assumed to be a uniform distribution over all possible microstates that satisfies a few constraints, such as the value of the energy, the number of particles, and so on. This is very similar to the principle of indifference in classical probability, which assigns equal probabilities to outcomes for which there is no justifiable preference.
For example, if we have a fair die, meaning that the die itself and the mechanism for throwing it do not have a preference for any side, the principle tells us to assign equal probability to all sides. There's a footnote. The principle of indifference is often stated in terms of degree of belief. It is the agent that has no reason to prefer one outcome over the other. We state it in more objective terms. The system and preparation procedure do not have a preference. If an agent believes a die to be fair, while in fact the die is loaded, the principle of indifference gives wrong empirical results, and therefore for us it does not apply. If the die has 6 sides, we assign probability 1/6 for each side. The part of probability theory that is linked to combinatorics works like this. Note that what number we use to label each side of the die, or whether we use something else, e.g. poker dice, images of playing cards, is irrelevant for the probability assignment. Therefore, when applied to discrete variables, the principle of indifference is invariant under relabeling.
If we try to apply the same idea on the continuum, however, things are not as simple. Suppose we have a factory that produces boxes at random with sides from 1 to 3 meters. Furthermore, let's assume that the manufacturing procedure does not have a preference for the size of the boxes. Using the principle of indifferences, we assume a uniform distribution for the side from 1 meter to 3 meters. However, we could have equally said that the factory does not have a preference for the total volume and assign a uniform distribution for the volume from 1 meter cubed to 27 meter cubed. The problem is that x to the function x to the third power is a nonlinear transformation, and uniform distributions do not remain uniform under nonlinear transformations. Another way to frame it, on the continuum, we do not have a probability, but a probability density, which has units of probability over units of the variable. In the first case, the units were probability over meters, while in the second, probability over meters cubed. The density then is unit dependent. It depends on the variable. This is, yeah. This is essentially our problem. Inside 1185, the densities over continuum variables depend on the choice of variable and therefore do not in general satisfy the principle of relativity. If we have a uniform distribution over a variable, it will only remain uniform under linear changes of variable. This means that density, thermodynamic entropy, information entropy, all the properties we looked at before are not the same under variable changes. Mathematically, the issue is that only transformations with unitary Jacobian preserve these properties, which is not generally the case.
How does phase space solve this problem? Phase space is defined by two variables, q and p. A change of coordinates only changes q arbitrarily. Once the q change is determined, p changes as a covector. Around each point, we have the q hat. So take the derivative with respect to the original position.
Yeah, this is just a chain rule
Yeah.
for the differentials.
Which means
and the
that
second one is the transformation rule for the covector.
And then we have the area of phase space is the same.
Yeah.
The area is conserved under generic change of q precisely because p changes in the opposite way. And there's a footnote. In statistical mechanics, it is often said that Louisville's theorem justifies the use of phase space volume as state count. Louisville's theorem states that under Hamiltonian evolution, the density, or equivalently the phase space volume, is conserved, which corresponds to the assumption determinism and reversibility. As we mentioned before, the conservation of volume and time would not be physically meaningful if the volume were not first an objective quantity. Therefore, Louisville's theorem does not justify the use of phase space volume as state count. It is the invariance under equal time coordinate changes that does.
And we can go back. Yeah.
Well, the math is clear. What is the physics behind this? Why does conjugate momentum magically change when we change position? This is better understood if we think in kinematic variables, position and velocity. Why would velocity change when we change position? Because units of velocity are units of position over time. If we redefine units of position, we will redefine units of velocity as well. As we said before, the mathematical tools we currently use do not capture all the physical elements, and unit dependence is something that mathematics currently fails to capture. The defining role of coordinate variables qi is not that they describe position, but rather the following. Inside 1.188, the coordinate variables qi define the unit system.
So this is actually like the trick, the core trick that we use here. So the QI defined as configuration space, right? It's we basically say they don't just define a configuration space where I don't know what it is. They define the unit system. So that's their primary role, and everything else that now has to change in sync. Because whenever we change the unit system, you're going to have derived quantities, and all the derived quantities have to change in a particular way.
Okay. What are the units of conjugate momentum then? Given that the product dq dp is invariant and it measures the count of configurations for 1 degree of freedom, pi must have units of configurations divided by units of the corresponding qi. By convention, we measure phase space areas in units of angular momentum, in units of action h. But why do we do that? Suppose that we track position by an angle in radians, q theta. Conjugate momentum p theta will be expressed in units of area of phase space, and therefore angular momentum. This is the connection between angular momentum and phase space areas. The conjugate of a dimensionless quantity must have the same physical dimensions of areas of phase space. However, if we change the angle from radians to degrees, conjugate momentum will be units of h over degrees. That is, it is improper to say the count of states is expressed in units of angular momentum. Moreover, while two quantities that represent the same physical quantity must have the same physical dimension, the converse is not true. In general, units and physical dimensions keep track of some aspects of physical quantities, but not everything. For example, one can show that dimensionally pressure is equal to energy over volume. This relationship is actually useful when describing fluids. On the other hand, energy density is another useful quantity to, for example, measure the capacity of batteries. There is no relationship between the energy density of a battery and its pressure. Another puzzle. If one multiplies radians and meters, what is the resulting unit? Consider the area of the side of a cylinder section, theta RH, where theta is the angular size of the section. R is the radius and h is the height of the cylinder. If we multiply theta and r, we get the length of the arc, which is the distance. We get meters. However, if we multiply theta and h, we do not get a length. We have an angle times length. We get meter times radians. The issue is that an angle is really a ratio between lengths of the arc and the length of the radius. Only a multiplication by the correct radius will give back a distance. Okay, that was 41. Ultimately, areas in phase space are measured with those units because in an inertial Cartesian coordinate frame, linear kinematic momentum times distance can be used to count the configurations of the system, as we saw when discussing the full kinematic equivalence.
To recap, we saw that we cannot define a coordinate invariant density over a single continuous variable, but we can do that over two variables if one has inverse units with respect to the first. Is this the only case? What happens if we use 3 or more variables? Suppose that Q is the only variable that defines the unit system for a set of states, meaning that all other variables have derived units. Then under unit change, Q hat equals Q hat Q. The units of all other variables must be uniquely defined. Suppose that we add a single additional constraint, that the measure of states is invariant. How many total variables can the state space have? We saw that there must be more than one variable, or we cannot change the unit arbitrarily. Now suppose that we have 3 or more variables. Given that we have only 2 constraints, the choice of unit change and the array conservation, these are not enough to fully determine the transformation of all variables, and therefore the units of all variables. Therefore, it would not be true the units of Q fully determine the units of all variables. There's a that did, right? therefore it would not be true that the units of Q fully determine the units of all variables.
Sure.
This tells us that to have densities that are invariant under equal time current changes, a state space for a system that is fully characterized by a single unit must have exactly one additional quantity, conjugate momentum, that changes covariantly under unit change. We reach the following inside 189. Degrees of freedom are two-dimensional because only these allow coordinate invariant densities and count of configurations.
Invariance over multiple degrees of freedom. We saw how things work for a single degree of freedom. Let's see how they generalize for multiple independent degrees of freedom. Suppose states are identified by m variables. You said C.
Mhm.
But the unit system is fully identified by a subset Qi of n variables. This would be the case, for example, if we are studying particle trajectories as the spatial variables define the unit system. Moreover, suppose we assume independent degrees of freedom, that the system is decomposable into independent degrees of freedom. In this case, independence of the variables ties in with the independence of the degrees of freedom. That is, if the unit of one variable depends on the unit of another, they cannot belong to independent degrees of freedom. On the other hand, if two Qi define independent units, they must belong to independent degrees of freedom by definition.
For example, suppose we have 3 degrees of freedom, then we must have 3 variables Qx, Qi, and Qz that define the units of each degree. Suppose we change Qx to Qx hat while leaving the others unchanged. Given the premise and what we've discussed above, there must be another variable Px plus inverse units. This must be an additional variable given that Qy and Qz must have different units. Given that the degrees of freedom are independent, we should also be able to fix the value of both Qx and Px and obtain a subspace identified by all the remaining variables. Now suppose that we change Qy by itself. By the same logic, there must be another variable Py. This must have units of inverse Qy and therefore cannot be any of the variables we already have. We repeat the logic and we find another variable Pz. At this point, there cannot be other variables. We would have to introduce units that do not depend on Qx, Qy, and Qz, but this contradicts the assumptions that Qi define the unit system. In general, then, if we have n degrees of freedom, we must have two n state variables. The Qi's that define the units and the conjugate quantities Pi expressed in inverse units.
We now want to introduce a form omega AB that returns the count of independent configurations for an infinitesimal parallelogram. Here we simply use the same arguments that we gave discussing assumptions I and D, independence of degrees of freedom. The number of independent configurations identified by a parallelogram within the same degree of freedom will be given by the area of the parallelogram. On the other hand, a parallelogram across degrees of freedom, for example, formed by delta Qx and delta Py, will not properly identify independent configurations. Note, in fact, that their product is not unit invariant. This means omega AB must match the familiar form. In short, assumption I and D plus requiring that the count of states is the same for all equal time observers gives us the structure of phase space. That is condition PS inf. The space allows coordinate invariant distributions over equal time independent degrees of freedom is equivalent to the assumption that the symplectic form is invariant, which implied covariance, and what was POI?
Poisson.
Poisson, okay. To be preserved Poisson brackets. Yep.
Phase space and its structure then are neither a coincidence nor a choice. Phase space is the only space that allows us to define key concepts like uniform distributions or reversibility in an invariant way, which would otherwise be ill-defined over the continuum. In other words, inside 190, the structure of phase space is exactly the structure needed to define state densities, thermodynamic entropy, information entropy, and statistical uncertainty over continuous quantities in a way that satisfies the principle of relativity over for equal time observers.
The
Okay.
The structure of phase space then comes out from simply keeping track of unit dependence between variables. This should sound familiar, as unit dependence was used in condition full kinematic equivalence unit to motivate why assumption kinematic equivalence should be implemented in its full form. Linearity?
Yeah, it's a linearity between momentum and velocity.
The existence of a metric tensor of inertial mass and more could be seen as stemming from assuming that the change of variables from dynamical to kinematic variables depended only on position qi. Now we see that the very structure of phase space rests precisely on the fact that coordinates are those variables that define the units. This leads to the following observation. While taking the weak kinematic equivalence invariance of assumption kinematic equivalence leads to no mathematical inconsistencies. It would be physically inconsistent. On one side, when defining phase space, we are saying that the units of the coordinates qi determine both the units of velocity and of momentum. On the other side, when introducing weak kinematic equivalence, we claim that the coordinates qi do not determine by themselves the unit transformation between velocity and momentum. The fact that we can write a mathematically consistent model that is physically inconsistent is evidence that we need a better mathematical specification of our physical theories. Namely, we need a way to encode unit relationship between variables.
We are also now in a position to answer another question. Why are the laws of physics second order? That is, why is it that external forces specify the acceleration of the system and not the velocity or the jerk, i.e. the derivative of the acceleration? Note that once the structure of phase space is derived, we know that under kinematic equivalence, position and velocity fully determine the state, and during the evolution, the change of state is fully determined by the acceleration. In other words, the laws of physics are second order exactly because the state is given by variable pairs. Since we have an explanation as to why the state space must obey that structure, that same explanation tells us why the laws are second order. Therefore, we have inside 1.191, the principle of relativity ultimately requires the laws of motion to be second order. The principle of relativity, then, is responsible for much more than the invariance of the laws. It is also responsible for the structure of the space and the nature of the laws themselves.
So we are at the hour. I think we are going to stop here and see if there are questions, comments, or anything.
Have you found like some kind of satisfying way to actually encode units in the mathematics? Is it like
Absolutely not. I don't even know exactly what they are. So the simplest way would be sort of to make a tag somewhere. So every time that you have a real number, you have some tag that tells you that you have units. But even that, I don't think it's enough because so I do not even understand how when you start having a nonlinear transformation, what a unit actually is. And because you lose additivity. Like when we think about units, we always imagine that twice the amount of the units is twice the amount of the unit. But if you have a nonlinear transformation, that's not what happens. So you have to start thinking, like when you do general activity, right? You can imagine that you basically just have goalposts, and then you give a number to that goalpost, but that number is not really a distance anymore. It's just the position of your goalpost, and then you see that there is a relationship between those positions and the actual distance. And so yeah, I quite frankly haven't. We tried something even more lower level. So we have this other part of physical mathematics where we start with assertions, like with statements and verifiable statements. So the idea was to give a unit to those statements, and essentially to how precise they are. Like the more precise, the more refined, and then you can basically say, now I have an equivalence class of statements that have sort of the same precision, and then I can talk about a unit by fixing one statement and saying this is my reference statement, and then the precision of all the other statement is measured is in effect with relationship with that statement. But that was too general, and we were never able to get it up. So yeah, I don't quite know exactly how to do it yet.
Units are
The
weird.
on So the only thing I thought about, and I think Gabriele, you mentioned it in some video, and I was very happy that like the thing I thought about and no one ever said, finally someone said it on YouTube. So when you have, they say everything that is can be expressed in meters, you can add a length and a length. You can use meters for that, and you can
Yeah.
multiply it by a scalar. You cannot multiply a meter by a meter. You get a
Right.
meter squared, right? So the structure you have is you can add and you can multiply by a scalar. So that's a vector space, right? And then you can ask yourself, how many linearly independent elements do you have? Well, you have only one. So your space is like a one-dimensional vector space. And when you pick a basis, you pick a unit. So you say, this is my reference, my basis vector, and then every length is a multiple of a meter, So you can literally think of a meter as a basis vector in a one-dimensional vector space. That's at least, well, you have some mathematical structure. It doesn't capture the full thing, but it captures many nice things. For example, you can also think of density as a linear functional, right? If I want to measure density on a volume, you need to give me something in cubic meters, and I give you a number. So then you automatically see like a density is in a dual space, and it will have units inverse cubic meters. And you can, if you have meters times, like a velocity would be meters over a second, and then I think you get the tensor product. So you have tensor product of length and then the dual of second. And then you
Yeah,
would get the units meter over
that's actually a
second.
mixed tensor. It's something that takes units of time and gives you units of space. So it's a map between time and space. That's how I think about that.
Okay.
So a velocity is something that you can give it a dt and it gives you a dx.
Yeah, true.
Right. So yes, so all of this works very well. You're right. I should have mentioned that, and it's sort of the basis of the reconstruction of all of the differential forms and all of that. And it is very nice. And you're right, I shouldn't discuss. Sometimes I get fixated on the general solution where, maybe I should like be a little bit more humble and accept that we have a very good solution. But again, this all works because of the linearity. As Tobias was saying, you have
Yeah.
a linear vector space. So for that, yes, for that we have a solution. You're right.
Yeah. Which I guess if you have coordinate transformations that could in principle like be nonlinear, like from x to x cubed, you obviously change the unit somehow.
Yeah.
Maybe this is just there will be kind of a transformation on a manifold, but then on each tangent space, you would make
Exactly.
it linear, right? Then it makes
Yeah.
sense again. But
Yeah.
on the manifold, I don't know how to deal with units then.
Right. So
If you can do
the point
anything.
is exactly that, is that when you do all the linear structure, even in the symplectic form, right, you're doing that, the relationship between the units of Q and P becomes linear in a neighborhood, like when in a
Yeah.
sort of a semi-tangent, yeah, because you're doing vectors, and so you basically think that everything becomes linearized at that point, but then every time that you move from one point to the other, you have to kind of change this
Yeah.
linearization, and differentiable curves are exactly those curves that can be linearized in the same way in all coordinates. So that if you had a kink of a curve, right,
Mm-hmm.
then and you go and use a non-differentiable transformation, you can make that kink a line, like, because you with a non-differential transformation you can change the angle at a point, and then you are like breaking essentially that linear structure, because now the lines do not continue in the same way. And so all of differentiability essentially is there to preserve that linear structure. So if you say, I want to be able to define units at least like nicely in a neighborhood, then you must have a differentiable structure. So this is another link of how units requirement actually becomes requirement in the more mathematical sense. So you're right, Tobias. We have actually a lot more. It is not fully general, but it would probably be enough to already justify a lot of structure that we have in math, right? All the variance and covariance are basically unit transformations. The fact that you have the differentiable structure is the fact that you can talk about units in a meaningful way in a neighborhood and so on. And then, as you said, forms are things that take the inverse, but in general, tensor, right? If you have a tensor, the index up is because the tensor is going to spit out something that is proportional to that unit. And if the index is down, then the tensor is going to take something of that unit and make that unit disappear.
Yeah. That's in fact how I remembered that vectors are contravariant. Because if you reduce to a one-dimensional vector space, it's just the same as units. It's literally like, well, if I have something meters, if the meter gets multiplied, then the value gets divided. It's contravariant to my change of basis, which is a change of units in one dimension. Yeah.
Yeah, it would be a good, maybe I should make a video of all this, because, yeah.
I think that could be very popular, yeah.
Yeah, I think so.
Well, maybe somebody can help me create the slides. Anything else? Then we stop it today, and next week I don't think there are any problems on my side. Let me check my schedule. Yeah, I don't think I have anything. So
Yeah, I know that I won't make it next week, but that's all right.
well, that's why we have the recording, as long as at least a couple of people show up. Okay, so see you next week then. Bye, everybody, and thank you for watching.
Bye.
Have a nice week.
Bye. Have a nice week.
There we go.